Great. Well, welcome back, everybody, and welcome to new people. So what I wanted to do, the first lecture here is, I guess, eventually just review some of the logistics, make sure we're all synced up, but also do a bit of a reprise of the last quarter and talk about some of the same things that we talked about at the beginning of last quarter to see if there isn't sort of a different perspective that we've gained about them. So, and then I'll also try to make some more general comments that get folks that haven't been here in a while or that are new, so reoriented. Right, so the kind of central motivation of the two-quarter sequence is to, first of all, appreciate how complicated the world can be, and we studied some nonlinear dynamical systems and chaotic systems as examples of that, just examples. And then the question comes up, well, how do I describe the complicatedness of these systems? And part of that answer is to first think carefully about how we measure systems. So I introduced the idea of symbolic dynamics. And then we end up with basically a process, a series of measurements, a time series. And we tried to figure out, using sort of existing tools, namely information theory, what we could do with that. And so we ended up at the end of the winter quarter, with a set of various characterizations of different kinds of information storage and processing. However, what I want to talk about today is a little bit of a critique of that and what it doesn't do. So last quarter, I was a big booster for information theory and how it helps us deal with systems with arbitrarily long-range correlations, apparent organization, apparent information storage, and but how it doesn't really get down to the big question. So today what I want to do is a little bit of review, again, hopefully rethinking this now that we have some information theory under our belts, and then to repose the questions that we just came up to at the end of the winter quarter. So if you remember way back 10, 12 weeks ago, I tried to frame some of the motivations for the class in terms of the history of the Industrial Revolution, right? So we're thinking here, remember back to the mid-1800s and how there was this huge efflorescence in the sort of technology and engineering, and slowly the science and theory of these engines, these heat engines, things that converted heat into mechanical work. And this caused a huge transformation in society, right? No longer did humans, the product of their effort, be proportional to the amount of physical effort they put into something, right? Up until that point, everything that you ate or that maybe you used horses to help a little bit was pretty much in proportion to your own physical effort. Now suddenly we had these new devices, steam engines in particular, that could amplify that, where we just had to design them, and then the source of energy was the heat, and convert this abundant source back then, coal energy, into heat and then into useful work. Of course, this was a wonderful thing, and it was also a terrible thing. So like most scientific and technological innovations, technology giveth and technology taketh away, right? So you can think of the time of Charles Dickens and these huge factory towns, people spinning yarn, these huge rows, all driven by steam engines, of course, but kind of a new kind of industrial labor oppression came out of that too. In addition to, at least for some classes in society in England at the time, becoming quite rich because of this amplification. And the interesting picture, though, if you study the history of that, is that it's not like physics came in and said, oh, let's come up with a theory of converting heat to work and what the limitations are. Oh, good idea, let's build a heat engine. It was pretty much the opposite, or probably the fair picture is very much an interaction between what you might call engineering and free commerce, invention. An important part of the acceleration, or maybe I should say stabilization of the industrial age, was the invention of the patent system. It was really critical. That stimulated people to actually compete with one another, and they could get credit for some period of time for the inventions they had, and therefore compete and move ahead of others. So there was even kind of a change in the legal system that was important for this all to work. But it wasn't, theoretical idea, let's build a device. It was very much this interaction between having invented the devices, the steam engines. People noticed as they tried to improve them that there were certain limitations they kept running into, and this led a whole host of now famous what you call physical scientists, Clausius up to Maxwell, Boltzmann, and so on, to try to figure out what's going on. What are the physical principles that lead to the conversion of heat energy, something like disorganized energy, into organized energy, work at the macroscopic scale that can be harnessed for doing things. So we see this period of a century, more than a century, of this interaction between the development of the science of thermodynamics and the theory and the engineering of the Industrial Revolution. So if you remember, the question I posed was, well, what age are we in? Right? We're sort of in the age of information, or at least that's what, Time magazine, they should probably put the bit on the cover page or something at some point. But so we keep hearing about all of this information age. And of course, that language goes back at least 50 years, right? So this is, in a sense, not terribly new, but it does sort of bring up this puzzle of what's the corresponding scientific basis for the information age. Certainly there's a lot of engineering, right? Universities have very wealthy departments of engineering. Some of them are oriented around computer engineering and computer science, so-called. But that's the engineering side of information processing devices. And how is it, though, that we can look at a physical system and understand how it's storing and processing information? Where's the physics of this, the corresponding theory that would be the analog of what thermodynamics and then statistical mechanics right afterwards came to be, to give it's basically a scientific, theoretical, and predictive, more importantly, predictive foundation for heat engines. So that's kind of the largest, if I paint the largest picture, and hopefully you're, well, since we're 10 weeks into this, some of you are halfway convinced that there might be some analogous theory here. So part of the discussion is just trying to frame it, thinking about what theoretical tools and concepts we have to think about the information age. Right, we have these devices, wonderful little devices here. They are at sort of one and the same time information processing devices, and that's the way the computer engineers and software engineers look at them. And in particular, if you're trained as a software engineer, you don't even think about the physical basis for this. The fact that this thing gets hot, that's certainly a concern to the chip manufacturers, the people that design the integrated circuits. And the heat dissipation is the principal reason these devices have stopped getting faster, and that we now, to keep people buying new versions of them, we just add more CPUs and make bigger chips. But the areal density of information processing hasn't changed, so because of heat dissipation. So there's obviously an important connection between how much information processing this thing can do and its physical instantiation, right? Now, as a natural scientist, you would look at this and go, oh, it's a physical device. This is a physical phenomenon. How does it store and process information? Are there basic principles of that would correspond to the 3 laws of thermodynamics? What would be the 3 laws of information dynamics for physical processes? And then you can kind of imagine, if you want to get a little bit speculative, well, I don't have to think about these designed physical devices. I mean, they're examples of things that process information. But you could also look at other physical, chaotic, nonlinear processes and ask, what kinds of information processing are they doing? I mean, you may not be able to run, Excel on a waterfall, but it's still a reasonable question to ask. As the waterfall is behaving, it has a certain kind of organization, right? There's some laminar flow at the top, there's spray over here, there's a water crashing at the bottom. At some moment in time, that physical process remembers its history. Well, and forget some of it too. It's also a turbulent fluid, it's chaotic, so it's also itself creating information, excavating very small amounts of thermal fluctuation to macroscopic scale to actually place the water drops and the water flow in this unpredictable way. So it's a fair set of questions. How much history does the waterfall store? How, in this turbulent snapshot of flow, how in the organization is that information stored? And then by what sort of dynamics does it take that stored information to produce future information? So that's sort of where we're going. Kind of a quick outline or unpacking of what the what means. So there's this contrast I'm kind of drawing, right? So conventional physics, in its maybe slightly unfair characterization, you can think of physics, what you're doing is you're suffering through your physics grad classes, or even undergrad physics classes. You're being taught that there are different kinds of energy. They get stored in different ways, and that these different kinds of energy get transduced into other kinds, right? So the example I use is, right, I'm now increasing the gravitational potential energy, and I could turn that into kinetic energy if I dropped it, which I won't. So, right, so that's what the different subfields of physics are, essentially an attention to different kinds of energy and energy transductions. So what's the physics of information? Well, we have a similar set of questions. I mean, if you didn't even have a new idea, you'd say, okay, what kinds of information are there? How do they get stored? And can I change one into the other? And so now, hopefully, when I said that before 10 weeks ago, it's kind of like, what's he talking about? But now that we've talked a bit about information in these nonlinear processes, we have some sense. There are different kinds of information, right? In fact, it's almost becoming an embarrassingly long list, right? There's the entropy rate. That's the rate at which the system creates information. We gave that a mechanistic or deterministic interpretation in terms of if the system we're looking at is a measured chaotic dynamical system, we had this geometric notion of Lyapunov exponents, amplification in the state space of small variations, and that was analogous to the stochastic process that we were looking at, the output of the instrument having a positive entropy rate. So we even had kind of a mechanistic interpretation of what this information production rate was. But we saw, back the very last week, that just because a system produces information in the current moment, some of that information is just forgotten. Call that kind of ephemeral information. But some of that created information gets stored in the system and has an effect on the future, right? So the analogy I drew was, imagine that you're listening to a piece of music, and there are many. We listen to music partly because it's surprising, so there's a certain amount of randomness and unpredictability that we find engaging. And there are random events that, for example, just sort of happen. You kind of go, oh, that's nice, but then it doesn't have any effect in the rest of the piece you're listening to. Or you can imagine random events like shifting the scale or doing a chord change. That actually changes the rest of the piece until it happens again. It's a random thing that happens, and it changes the context for all of the future tones and notes coming out of the musical piece. So there are different kinds of information. So we can ask what kinds are there, how they get transduced, and basically same set of questions, except we've just changed from an energy view to an information view. Now, of course, these things that we're talking about, the objects we're talking about, like this thing here, it's sort of same device, same phenomenon. So we can, ask, well, okay, there's a certain amount of energy processing. If I put my hand underneath the bottom here, it's not too bad. It's a little warm. But what does that have to do with the information processing of putting this image up here? So there's this question of how these views are related. How is energy related to information and vice versa? And they're just simultaneous and complementary accountings of the same phenomenon. So in some sense, there has to be some relationship between them. But I think the first fair thing to do is not assume anything at the outset. So you'll remember this, and I want to kind of talk through it again and see if you have a different perspective. So the first claim is let's not conflate the two things. In fact, there are many arenas in which there is a conflation between concepts of energy and information. For example, just to pick one, in machine learning, there are many interesting techniques where there's an analogy that people draw between changing parameters in a model and having the model come to equilibrium with the data when it finally describes it well or up to some error. And that is actually a conflation of these two concepts. If you actually look at the mathematics, you'll see information on one hand, probabilities, and of course minus log of probabilities, that's information. And then that's related to an energy, and people now think of learning as moving down, minimizing some energy on a surface. So this is actually sort of a non-trivial statement up here. Depending upon the context, it's either outrageous or obvious. So let's go back to this. You'll remember it as soon as it starts out here. So very physical system, right? So we're looking at energy. But of course, how this chain has been set up is to be very delicately poised at a number of these points, such that not that much energy is actually transmitted. Nonetheless, as we go down the chain, there are huge effects happening. Well, huge relative to how much energy is transmitted from one contingent stage to another.
Isn't it nice when things just work?
So I hope you were looking at that with kind of a different perspective, right? Okay, so for me the first thing to say about it is I kind of imagine that they're all these stages. I don't know, what, like 30 of them. All very delicately designed. I can't imagine the number of takes they had to do to get that to work right. But each of these contingent stages transmits only a fraction of the, say, kinetic or gravitational energy. Whatever it is, they're different things. And presumably we could all sort of go through the movie and figure out where the energy is stored, how it's being transduced in the next stage. But if you have 30 stages and you're designing each one of these contingencies to just transmit just the smallest amount, say 1/10, then you get very suspicious of this energy accounting as an explanation for the car rolling off. I mean, come on, that car weighs 3,500 pounds and it rolls off and stops, right? And there's friction there and everything. How much of the initial little tweak that the sort of off-screen person gave, that initial energy is responsible for rolling a 3,000-pound car off a ramp? Well, if each, in this simple picture, if every of the 30 stages only had 1/10 the amount of information, we know how much energy is left over. That's 10 to the minus 30. In other words, that's arbitrarily small, right? 1/10, 100th, 1,000th, every stage, right? There's something else going on here. perfectly plausible, understandable, entertaining. So what is going on? So dynamically, what's going on? In a sense, this is like a chaotic system. Every one of these contingent stages is taking some very small effect, right? There's some phenomenon that they've engineered and poised so that a small incoming perturbation will lead to a large effect. So like one of the curious ones is, I mean, many are, but you remember there's a ramp with tires on it? The tire rolls up and just hits the bottom tire on the ramp, and it rolls up. Well, how did they do that? Well, what they did is they, of course, put a mass, they positioned it with a mass on the inside of the tire, poised so that it could sort of roll uphill. Yeah? 607 takes. Okay, yeah. It must have gotten tedious after a while. So partly what you have are each one of these stages, there's some kind of stored energy that then can be released by sort of the smallest little perturbation coming in, right? And the more delicate each stage is, the more impressed we are, right? I mean, that's part of the... So there's something else going on. And we understand that moderately well because each one of these contingent stages, it's like an amplification. It's like the system is poised at an unstable fixed point, right? And then as it gets knocked, it falls off the fixed point and then goes to some other fixed point and releasing this energy to move forward. So it's not, before when we were studying chaotic systems, we imagined steady state system where we're on some attractor and we're in the flow in the state space is constantly doing that same kind of amplification. But here, what they've done is they kind of laid that out in space. A little instability here grows, causes, it kind of dies away, but then there's enough left over that it can cause the next thing to happen. And each one of these is an instability very much like the ones we were studying with the chaotic attractors. Except that was just kind of one process, if you will. So information is being created as we go down there. So we have this macroscopic effect. We observe this event. There's information. We're surprised. In fact, they were probably really happy after the 607th take to get it right. Talk about a chaotic, unpredictable process. So there's something else going on there that's not well accounted for by the flow and storage of energy. It's part of it, but there's something else going on having to do with this a series of instabilities being built into the chain. So that just, again, I'm just trying to problematize the issue of how we develop causal explanations for the processes we see around us. And there's part of that causal chain we just saw, there's an energy accounting, and part of it is an informational accounting. So now, when we started out in the spring quarter, the first part was really focused on nonlinear dynamics, trying to understand in a much simpler setting what we just saw in a chain, namely this deterministic chaos. The sort of this is like a Zen koan, you know, that you had processes or systems that were stably unstable, right? Constantly amplifying small variations. From afar, they're attracting, and we go to some place, rattle around on the solution set, but within the solution set, within the invariant set, it's unstable. So globally stable, locally unstable. So that's how we can now think about stable instability, and it informs a bit of the way we now think about that supposedly causal chain in the Honda ad. In fact, there's a name for that. Just to kind of indicate that it's a kind of spatially distributed instability. It's called a convective instability, and this happens in fluids a lot. A fluid can be stable until it starts to flow, and then it creates a chain of instabilities. So we were just looking at that similar notion of instability, but in one process. So, and the lesson there is that nature, you know, even few degrees of freedom, even sort of weakly coupled together, actually produces surprise, apparent randomness in information, right?
So just, might sound kind of stupid, so the instability then is, and the stable instability is each part becomes unstable consistently? So I'm a little confused as to what's unstable in this situation.
You mean with the Honda ad or with
Yeah,
the chaotic
the
attractors?
Honda, right.
Oh, well, I mean, yeah. That's a little more complicated thing to try to describe because that is highly engineered. I mean, it's partly why I didn't even talk about convective instability. We just dealt with one chaotic attractor and how we had
Okay.
vector fields and flows that did an amplification.
Maybe like each part is a little bit of chaos and instability.
Yeah, well, but they well, it's somewhat stable, but it's not that stable because they still had to do over 600 takes, right? So as they're crafting this, they're trying to, I don't know, I don't want to get too metaphorical here, kind of crafting the vector field to keep it within bounds. But exactly how that exhaust, how the muffler rolls over and just comes up and hits, I'm sure they just had to, you know,
Just do a bunch
just
of
try it. Yeah. So, but there was definitely sort of they were engineering the stability. In some sense, there's sort of like a tube that was successfully traversed was the whole series of events, and then sometimes it would go off to another attractor and just stop. Right, the muffler goes it doesn't make it. So damn it, you have to go all the way back, reset everything, and yeah. So actually, the original idea for that was a couple of Dutch artists. It's called The Way Things Work. There's an earlier piece about 20 years old. Okay, so we had this. We have a mechanistic appreciation of how randomness and unpredictability can come to be in studying these chaotic systems. Right? Before the discovery of deterministic chaos by Poincaré, people just assumed there was this stuff called randomness that just existed. This is what you were playing with when you went gambling. So you even had people like Laplace in the late 1700s writing whole books on the calculus of probabilities, this delicate science of chance. And it was just stuff. There was no notion. I think people had an intuition for it, but there's no direct mechanistic notion that nature would actively produce instabilities in a stable way. But there's still this sort of puzzle, like what is information? That view brings up the question of, well, how do we define it? What's a degree of surprise? Shannon suggests his notion of information. And then where does this stuff come from? Then there's also sort of a flip side to this, of course, that not everything in the world is random. So you might conclude from the study of chaotic systems that even simple but nonlinear, weakly nonlinear systems, simple systems coupled together, can be chaotic. You go, okay, fine. The current picture of the world is a bunch of molecules, things banging around. Why isn't the whole world completely chaotic and disordered? So as soon as you start studying and appreciating where randomness comes from, suddenly you realize that can't be the whole story. Otherwise, we'd be like an ideal gas and all, you wouldn't understand what I was saying. We'd all be disassociated. So there's the flip side of the coin. Immediately, as soon as you start to understand how randomness can be produced, that it's not just something that God decrees exists, but there's a mechanism to produce it. The flip side is, how is it that the world organizes itself? And I kind of talked through at the beginning of last quarter these different examples, the Belousov-Zhabotinsky reaction diffusion system, right? This is a petri dish with 4 reagents put in with a kind of red-yellow indicator reagent, and every volume element in this thin layer starts to oscillate, and then those oscillations start to synchronize with each other. But distant regions can be in different phases of their oscillation, therefore there'll be boundaries between them where they disagree on what the oscillation should be. And you have these traveling waves and target patterns and so on. Now we talked a little bit about this kind of spatial pattern formation when we studied the cellular automata, which were a much, much simpler discrete state, discrete time, discrete space model of this kind of pattern formation. But it's all over the place. Bacteria that are on a petri dish with agar, They put some nasty chemical in there. They all sort of gang up together in these waves, sort of move away from it. This is actually stressed plastic. Remember the last time regular plastic, and you just keep stressing it, and suddenly it breaks, and you get this, somewhat random, somewhat ordered, self-similar structure of these channels. The von Karman vortex street, striping on animals. So in this context, the ordered, disordered, slightly disordered patterns are important for the ponies recognizing their mom. So these patterns can even have a social function, yeah.
Can you cite examples of Sierpinski triangle, for example, in nature?
Sure, yeah, there's a whole... Yeah, that's one thing I don't emphasize sort of fractal stuff too much. I do kind of mention it. The one context we do look at that idea is in the context of trajectories or orbits or measurement sequences. That the various spaces we're in are called Cantor spaces. They're all sort of self-similar. So, yeah, but not so much studying, mountain ranges or Romanesco vegetables or whatever. Yeah. But that's a related idea, and we touched on how you measure the partial dimension of those sets a little bit last quarter. So the flip side of the coin of the nature spontaneously producing randomness is that it also orders itself. So how does this happen? And this, in turn, brings up this question of what do we mean by something being structured or ordered? And this, I would say, these questions are much less well appreciated in terms of physical theory. I mean, we can visually recognize that these things, these very, very different examples are structured in different ways, but that is calling on a lot of evolutionary history that's built into our visual cortex, appreciation for some kinds of patterns in the world. So how do we give a more rational, foundational and quantitative way of measuring organization, structure, regularity, so on, all these different words that need some kind of... And we started to think about that a little bit using information theory. Using, for example, when the main idea there was like this kind of mutual information. It was sort of an informational measure of correlation between points of a system. We generalized that to talk about a dynamical system in terms of the mutual information between the past and the future, the excess entropy. Sort of hinting at the system maybe communicating some information from the past to the future. So that was a start. In a few weeks, we'll appreciate how impoverished that notion is, but it's a good hint that there's something around the corner. So we have two sides of the coin, and then there's a more kind of dynamical question, or evolutionary one if you want. How does nature, in its manifestations, balance the two? A tendency to order, a tendency to disorder, a tendency to make structure, a tendency to be unpredictable. Right? Not every system is completely unpredictable, not every system is completely ordered. Most of the things we see around us, in fact, one could argue the very nature of language systems that we use are a dynamic balance between a tendency to order and a tendency to disorder, right? So think about how we're communicating. A language system is basically delicately poised at the interface between these two extremes, randomness and order, right? There's a certain amount of, we have to share a vocabulary, we have to share syntax, so that's the ordered side of the spectrum, speaking metaphorically. However, it's, what I'm saying, I hope, is not completely predictable and ordered. It's not in the vocabulary, otherwise you would have just read it and not showed up today, right? Presumably I'm saying something that's sufficiently novel that you find it interesting and engaging, that hopefully I'm, not only that, I'm communicating something new that you haven't understood before. However, if I start speaking Swahili, I assume none of us in the room, that would be so random, completely novel and unpredictable, but it wouldn't be understandable by you. So you can't be completely random, right? So communication systems, language systems, are a great example in this metaphorical discussion here of some kind of cultural process that evolves over, minutes up to centuries, that produces a communication system that serves a useful purpose. It has a substrate of regularity and order in the vocabulary, pronunciation, the phonemes we use, the syntax, but to be useful, we have to communicate something new. So I have to say things that you've never heard before, or new ideas. So it has to be a bit unpredictable, a bit random, but not too much. So this is just a general question. How does, different processes in nature, how do they balance production of randomness and unpredictability against generation of order, organization, and structure? And sort of the largest issue we're gonna deal with here is what I call pattern discovery. So before, the way I was talking was we're kind of being the Einsteinian scientists. We're looking out at the world, and here's a system I'm trying to describe. And thinking about the basic principles that might describe what its organization is. But how do we ever come to know new things? Getting back to language example, can I communicate to you things that you've never understood before? I hope so. I mean, that's why we take classes, right? That's why we engage in cultural activities and intellectual activities. And the contrast I draw is what's more familiar, this technology called pattern recognition, right? So the example I used before was you call up American Airlines, if they're still in business, and say, I want to go from Sacramento to Chicago. And you're talking to a machine. And the machine has to sort of figure out what the pressure waves on the microphone that got converted into electric pulses means to you. Right? And the way it does it, of course, part of the design strategy is all of those voice recognition systems, they try to carefully craft the context of interaction. So that at some moment in time when you're talking to them, they've told you to say what city you want to go to. And then all the system has to do is distinguish these pressure wave utterances and classify them into cities. In addition, behind all of that, even once you've constrained that context to help improve the recognizability of what you said, there are speech engineers who carefully craft, and now I can say it and you'll know what I mean, hidden Markov models, just like we studied, that describe, they choose some number of states for a phoneme, like sh, like in Chicago. The system takes a Fourier analysis, breaks it into time windows, and looks at the most energetic Fourier components. And then there's a hidden Markov model down inside that's being calculated, and it tries to figure out what the probability is for the sh phoneme or the go phoneme, these different hidden Markov models, and which most likely explains or predicts that input, that utterance, the pressure or voltage waveform. That's all done by hand. That's all crafted by hand. Very tedious, especially for these systems like airlines and big services would use, where they're called speaker independent. And really, actually, the key idea is the first thing I said: crafting the context of interaction, so the system doesn't have to, detect that you were saying the Gettysburg Address. You're just going to say a city name. So that's pattern recognition. Namely, the system has built into it a vocabulary, a pre-engineered vocabulary, a series of templates, and then what it does when the data comes in, it matches against that probabilistically, calculates the likelihood that the data coming in was Chicago, and then if that's sufficiently high compared to all the other alternatives in this vocabulary, in this template, then it assumes you want to go to Chicago. That begs the question. So the question for us is, how do we discover new patterns, concepts, ideas, new patterns that we've never seen before? We do this. I hope it's happening now. Getting back to the language example, right? You're kind of putting things together. And that to me is the biggest mystery. Even on a very practical plane, it's extremely important. When I first, so if I pick some nonlinear dynamical system, the OWL system, some variation of the van der Pol oscillator, the whatever. Imagine you hadn't seen the Lorentz differential equations before. You don't know how the system's going to behave. And there's certainly a series of initially very straightforward tools, calculate the fixed points, all the kind of boring stuff you do initially, because you can turn the crank. It's very straightforward to do those analyses. But then you want to understand, what's the shape of the attractor, the things you hadn't really understood before. And somehow we come to do that. We actually do actively build our own vocabulary and discover new things. So in addition to maybe thinking about how we discover new ideas through communicating with each other, there's even a simpler context when we're looking at nonlinear, chaotic, and complex systems, how we come to learn about them. What's new?
We learn about them, or we make the computers to understand us when we say something new. For instance, a new city.
Right.
Chicago, maybe computer know about Chicago.
Right.
Maybe
Right.
a new city. We want to make the computer understand us, or we recognize.
Well, I mean, eventually both, right? So I'm unaware of any speech recognition system that learns new vocabulary. They have enough difficulty just getting cities correct in a fixed set. But what I'm hinting at here, if we can understand, first of all, what patterns are through information processing and so on, ideas, then can we understand that well enough that we in fact could design? I mean, the real test wouldn't be, I like that theory of pattern discovery. It would be, I actually understand enough what the mathematical definition, the formal aspects of pattern are, and I can calculate various quantities that I could write a program so that machines could innovate new ideas. And that to me is sort of if I had to think about how I would pitch this against the way people have approached artificial intelligence, this question of pattern discovery is sort of my version of that. I'm not personally so interested in how well a computer can play chess. I can kind of imagine how you'd engineer such a thing, and eventually with enough hardware and a team of 100 software engineers and giant databases and new technologies, and they can now, machines can be, I'd like to see a system that could actually discover new things. So that to me is the real kind of decision criteria for success in understanding patterns and this process of learning, adaptation, and discovery, right?
It sounds, I don't know if you take it the right direction, it sounds kind of like an expansion of the problem of induction, the way you're kind of stating it.
Yeah, it's like induction. Well, I'll go through some examples. I'm kind of throwing these things out. It probably sounds very philosophical and hopefully interesting. But there are some examples that we can go through that show you cases where you can go from sort of wrong assumptions, too limited a vocabulary, and actually expand it. So there's a notion, it's like hierarchical induction. And the example case is extremely familiar to us all. This happens at the onset of chaos in the logistic map. But I'll just throw that out there. We'll get there. But there's, well, we know actually that the excess entropy diverges, right? We went through that. It had a logarithmic dependence on word length. Remember, that was diverging. So it's kind of hinting that this past-future mutual information was going to infinity. Look at longer and longer words. There's more and more correlation in these long sequences. So what kind of information is that? It turns out it's highly structured. And if you approach that infinite correlation system with any kind of finite model, it's always going to be an approximation. So we're going to talk about how to use, it's kind of like a higher level modeling. You build models, you build better models, and they grow, and you look at how they grow. And in the case of the logistic map, we're going to end up with a non-finite model of the information stored. But a nice descriptive thing where I can calculate everything, including various rates of divergence of the information stored. Yeah.
So I'm just thinking that, I mean, in this theoretical framework, if we do come up with an algorithm to discover new patterns, how do we adequately test for things like overfitting that
Yeah.
other
Right.
machine learning
Right.
could fall into?
Really excellent point. So yeah, in fact, it lets me, right, so the question is overfitting, right? So what is overfitting? Well, if I have 100 data points and I fit it with a straight line, I'm going to have terrible error if it's a random scatter of points. But if I use a 100th order polynomial, I'll have no error. But that model doesn't generalize well. So there are different ways of monitoring and characterizing overfitting. What we're going to do here is not really talk so much about the effects of finite data initially. What the goal here is to talk about what are the foundational concepts that let us define clearly what pattern is, what organization is, what models are. And then once we understand the kind of substrate of the different kinds of model classes, then we can come back and say, oh, well, if I only give you 1,000 measurements, how good is this model going to fit? And then we can come back to overfitting and underfitting and that kind of thing, and generalization error. Once we know what the substrate is. A lot of the work in machine learning, when it's trying to characterize overfitting, there are often these very implicit assumptions about a model class that gets fixed ahead of time. So, finite state hidden Markov models with 10 states or fewer. And then you can study, oh, well, if I have two data samples, I'm obviously not going to infer the transition probabilities very well. But there's some kind of trade-off. But what we're going to do is try to give a kind of a model class independent view of what structure is. And then we'll come back to thinking about, in practical cases, how we can infer things. So we'll likely have a couple lectures on Bayesian inference for the class of models we develop. But first it's going to be kind of, in principle, infinite data, not going to worry about statistical or sample fluctuations. Just what are the basic principles first? And that's a bit different than what if you go pick up a book on statistical learning theory. Yeah. Okay. So, right. So now a little more drilling down a little bit about kind of the outline of how we're going to, well, where we've come from and where we're going, right? So kind of so far, nonlinear dynamical systems that produce structure, they're attracting, stable, and chaos, unstable. We talked a little bit about self-organization in spatial systems, but even the chaotic attractors are examples of what a spontaneous organization, just the very flow in the state space down to the attractor is an ordering for us. And then once you get on the attractor, there might be this Positive-Lyapunov exponents and instability and therefore unpredictability, but the initial flow corresponds to the emergence of order. I can start from any random initial condition. I'm going to end up in this part of the state space. Just that simple transformation, visiting a small part of the state space, is an ordering. And then, well, the chaos is just, some of these nonlinear systems can be, have built-in instabilities. So we need to talk about those two things. And we have a bit of a survey of what emergence of order, emergence of chaos can be. What we're going to do this quarter is talk more directly about computation, storage, and processing of information, and the basic ideas we need. So kind of tie that back up. So the first winter quarter was really just dynamical systems, this mechanistic view of how you can produce order and randomness. Used information theory as the first step at quantifying this and trying to get a handle on these properties of information storage and processing. And the spring is going to be what I call computational mechanics. It's taking statistical mechanics and thinking about going beyond statistics and asking how mechanical systems store and process information directly. And we're going to learn some new things. I'm going to completely recast information theory. Practically, we're going to end up with very efficient algorithms for calculating all the things we've been calculating and that you are calculating in your homeworks tediously. See, you missed this. You had it last year, right? I mean, before I've said, oh, calculate the word distribution and then plug that into the block entropy and take the derivatives and all that. And well, as you know, in the homeworks or the final exams, kind of tedious. Well, it would be nice to have a framework, a model class, where you can calculate those things directly. So there's not only going to be sort of rethinking what it means for any system to store and process information, think more directly as mechanisms that compute, but also we're going to end up with very practical ways efficient ways of calculating these information quantities. So how are we going to approach this? Well, we're still on this diagram, right? Right? This is, head inside the box. That was the dynamical systems. We spent a certain amount of time with the symbolic dynamics, how you design instruments. Then we had these, almost the way I presented, binary processes over binary alphabets, and then we tried to characterize them with various kinds of information measures. So what's that leave? This next step. But at least up to this point, it was a fair, I'd like to argue, it was a moderately complete analysis, right? We had this tableau we came up with. I mean, I sort of simplified things by sort of focusing on just the block entropy and how that grew as a function of the word length L. Again, somehow we have to start with a word distribution, but then it's just simply, applying Shannon's formula to the word distribution of words of length L. We get this number out. And recall, the benefit of this is, again, also very practical. Instead of a bag of an exponentially increasing number of words and their probabilities, we just have this scalar number. So and it just kind of measures how flat the word distribution was. Okay, so this grows. Right? Longer sequences have more information, it grows, and then we have this linear asymptote with the excess entropy being the offset, and the growth rate being the information production per unit time, the entropy rate. We had the transient information here, which is the area that kind of control how quickly the h of L curve meets this linear asymptote. And then you remember we discussed how this is actually a measure of synchronization, how much information you need to pull out of a process to understand what state the process is in. So it was like a roadmap. Basically it was, 2-3 weeks of lectures, boom. So this tableau, very helpful kind of roadmap, which is the way, as you've noticed, I'd like to do things. Classifying, roadmaps, tableaus. And then the consequences we could draw out, right? Once we have this overall picture, there are different kinds of questions. So if you remember, so here's our block entropy curve here, and now imagine that we try to explain what's going on, but we don't know about this excess entropy thing. In a sense, we assume the process has no memory. So that means we're trying to estimate the slope here, which is the information production rate, the entropy rate, by a line that goes to the origin. And you can see, so this is now a memoryless source, an IID source, and it comes up and hits here with a slope that's larger than the linear asymptote, which allows the y-intercept to float. So the way we say that is if you ignore the fact the process is structured, you ignore the fact that it has memory, set e equal to 0, that turns into an estimate of the degree of randomness and unpredictability that's larger than the true. Right? So an agent that has inferior modeling capacity looks out at the world, can't appreciate all the structure that's out there, but to the extent it misses that structure, E in this case, that gets converted into apparent randomness. In a way, it's kind of moving in the direction of, okay, now I have the principles laid out, what kinds of practical questions can I answer? Okay, just like finite data sample would be another kind of way of thinking about this. How does finite data affect that underlying theory? And if you remember, all of that picture, the tableau, came from a very simple procedure of taking derivatives with respect to the word length. So we went from block entropy to the entropy rate, predictability gain, and then we integrated these derivatives to get the total predictability or redundancy, the excess entropy, and the transient information. So they're all systematically derived. Once I have my word distribution, I get my block entropy, and then I discover these various quantities just by taking derivatives. So, thinking back to the Industrial Revolution, there were different kinds of energy. We're trying to play the same game. There are different kinds of information, right? So we ended last quarter with all these different things. Measures of randomness or surprise, entropy of a random variable, or the entropy rate for processes that are not IID, that could have arbitrarily long-range correlations. We had to look at infinitely long words. Compressibility, well, that was related to the redundancy, log of the alphabet size, minus the intrinsic randomness per symbol. That's how much can be extracted out, compressed out. The transmission rate, right? We have information, transmission channel, shared information between the input and output. We applied that to thinking of a process or dynamical system. The shared information between the past and the future, that was the excess entropy. Synchronization was the transient information. We had the ephemeral information, right? That part of the spontaneously generated information that just gets forgotten. The system just throws it away. And then the complement to that was that part of the spontaneously generated information that gets stored and has an effect on future behavior. That was the bound information. So there you go. So like I said, that list is kind of getting a bit long here. But at some point, you'd start to see there's kind of a calculus for discovering these things. So that's, are starting to understand the different kinds of information, how they get transduced between each other. And that turns into a very practical analysis pipeline, which to a certain extent, the homeworks had been building up to, right? So if you're willing to take this at face value, well, the first thing you do is you have to figure out where your information source is. Maybe it's some dynamical system, could be cellular automaton, spatial system, could be some dynamical network, could be a high dimensional system, a low dimensional system, deterministic dynamic or stochastic, whatever. First find your system, and then you design your instrument. You sort of do your symbolic dynamics analysis so that you can get your informative symbols coming out of it. Then somehow, either, if you're doing this analytically, you calculate the word distribution, or if it was from some experiment, then you estimate these word distributions. Okay? And then you go through this information theoretic analysis to start to figure out what kinds of information there are, how random it is, how predictable it is, how much is stored, how hard is it to synchronize to, and so on. Right? So there's a pretty straightforward algorithm here that comes out of that. So we had, this sort of enriched sense of how dynamical systems can be complicated, right? We have the chaotic attractors. That's sort of a notion of state complexity and state space. We didn't really discuss it too much, although I did introduce it when we started, by way of talking about the general theory of dynamical systems. There's also complication at other scales in a dynamical system, basins of attraction, right? Over here in the state space, it could be a fixed point. Over here, limit cycle. Over here, chaotic attractor. So you can also talk about the complicatedness and the basins of attraction, and then also how complicated the behaviors change as you vary some control parameter. So a lot of the discussion was just focusing on these attracting invariant sets, and the chaotic ones were the most interesting. But there are also other levels of complication that you could ask about their role in storing and processing information, right? So we end up here with, through the symbolic dynamics, this rather direct mapping from dynamical systems, this sort of mechanistic view of what's going on in state space, thinking of the resulting behaviors as reflecting some kind of information processing. So that's all well and good. So now for the critique. Right? We have these ideas, a new sense of this wonderful diversity of different kinds of information, this kind of intrinsic semantics of that. They all kind of make some sense. Isn't that the end of the story? No, not really. Practically, it's just a pain to calculate all these things, essentially estimate them from the word distribution. And even maybe more basically, information theory never really says what information content is. And Claude Shannon, right, the inventor of communication theory, he was very explicit about this. This is the power of the theory. I'm going to tell you how much information there is, or how, being in an information source. I'll tell you what the mutual information is between the input and output of a channel, and I'll give you a theorem. As long as this amount of information in the information source is less than the transmission capacity of the channel, there exists a way of encoding that information such that you can get it through a noisy channel error-free. Never, ever once says anything about information content. Is that the Gettysburg Address? Is it the Encyclopedia Britannica? Is it some MP3 file? Doesn't matter. In fact, that's kind of the wonder of the internet. It doesn't matter, right? The net is supposed to be transparent end to end. But that's kind of a burning question. I mean, it does make a difference whether it's to me, whether I'm reading, the New Yorker or reading Gettysburg Address or article by Stanislaw Lem, the science fiction writer. It means I want more than just Shannon's operational interpretation of information, his quantitative approach. And the other thing is information theory doesn't really give us a direct measure of structure. Now you might say, well, now just a second. I can think of a process as an input-output, information transmitted from the past to the future like a communication channel. Isn't the excess entropy of that mutual information a measure of structure and organization? And I kept using the word memory, but you might remember also that I kept saying apparent memory, apparent stored information. There's actually a subtlety here we can't appreciate, that this sort of raw information theory view of a process, the sequences of measurements, how much shared information is there between the past and the future, that's inadequate. So we have to unpack this a little bit. The counterexample to the excess entropy being interpreted as the amount of information the process stores is that there are processes that are very, very structured, have lots of stored information, and have excess entropy arbitrarily close to zero. We call those the cryptic processes, so we'll come to talk about that. But this is sort of a more kind of direct motivation for looking for something more than information theory. And it really is to get to, okay, we have all these informations, now what? I mean, it really is to get to this. So this is all of spring quarter. What does it mean to build a model of a process? And again, we're going to do it kind of in principle. We'll worry about sample size and things like that. I mean, and what are these states things anyway? I mean, we've been using models. We had to, because it's so tedious just to talk about raw processes and sets of sequences and their probability. That's just tedious beyond belief. So we talk about Markov chains and hidden Markov chains and all that, just so we had transition matrices, things we could calculate with and talk about states. But that begs the question, right? I assume those models. The question in front of us now is, if I give you a process, a word distribution, can you figure out, actually, does the data tell you what the right model is? Not you saying, oh, it's Chicago, the first phoneme, oh, that's got to have 13 states and 12 transitions, positive probability. No, not imposing it on the data, but discovering it from the data. So how do you do that? What do we mean by state? I mean, it's kind of intuitive on the one hand. We use it a lot, sort of like saying system or something like that, or network. Everything is a system. Everything is a network. After a while, everything's got states. We really have to think more carefully about what states are. So that's actually the first kind of week or two, just thinking about what states could be. And can we extract the effective states given the kind of raw data of the process? So the way I look back at the winter quarter is that it posed a number of questions. And I kept trying to keep myself from, when I was describing things, of not, giving you the punchline. But we came up to thinking about, like, well, what is a model? Like I was just saying, what are the hidden states? If I have the hidden states, I've reconstructed the state space. Oh, Okay, you're emboldened. Now you think, oh, now give me the equations of motion. Give me the vector field over the state space. So can you get not only the state space, but also the equations of motion? That's pretty outrageous, right? If I give you some data, what I'm saying is, oh, here's a program. I'm teaching a machine how to build a theory. It's like, wait a second, I'm the theorist here. I write down the differential equations. What do you mean? I just give raw data to a program, and it spits back to me the theory, the set of differential equations, all the right-hand side, all the forces. It gives that to me. Well, it turns out you can do that. Now, there might be a sort of an objection. It's like, well, it depends, just like the speech engineers for American Airlines. They're making all sorts of choices. So to what extent, when we do these inferences or estimations or discoveries or whatever, can we get around the subjectivity of it? You know, do I always have to assume it's a sort of Markov chain of 12 states, or can I figure out the number of states? Is it always going to be dependent on the amount of data I have? Is there a way of ever getting beyond finite data to start figuring out what the truth is? Uh-oh, there's that word. Well, we'd like to think as scientists we do objective work, but a lot of what we do is steeped in subjectivity. Like, what experiment am I going to do? What do I like to do anyway? And do I want to sit in a dark room with the heavy magnets for late at night? So that's a lot, subjectivity all the way down. Of course, what I mean here is just I've got some data or description of a process. How much of what I understand about the randomness generating properties and the structure of the process is due to me making some assumption, and how much is actually the case? So we're going to work in a framework where we can answer those questions, where we can see that there's a difference between the subjective view and kind of an objective view. I already kind of talked about that a little bit when I was talking about how structure in the world, if you ignored that it had structure, that turned into apparent randomness for you. So we're actually going to come up with systematic ways of talking about degree of subjectivity. And to do that, we need some sort of foundation for representations for processes. So that'll give us a principled way to model processes in kind of a mathematical setting. There'll always be kind of finite data variations on this. So then once we start talking about this sort of principled way of modeling process, having the data tell us how the process should be represented, it brings up all sorts of interesting questions about cause and effect. Right? There's sort of a debate raging right now in kind of philosophy of science about whether you can measure cause and effect in an objective way, or whether you always need a human doing experimentation, kind of intervening in the system and moving components in and out. Well, that's an interesting idea, except the system, the very phenomena we're trying to study are systems that are coupled together. If I remove a coupling, I destroy its behavior. It might become non-chaotic. Then what kind of statement can I make about causal effects in a chaotic system if the paradigm is I have to remove components and see if they're important or not? When component removal, just like the study of life, many studies of life kill the life to understand something. It's the same problem. So very interesting set of questions. In fact, there'd be a great set of projects, even kind of almost philosophical projects about thinking about cause and effect in this current debate. And then sort of more practically, okay, what things can we actually analyze? There's one thing, I'll paint a very general picture of sort of the mathematical theory of doing these things. And it's like, okay, does it work for my system? And there are all sorts of different trade-offs and things like that. Finite data, do we have the right sort of representational system set up for this? What's analytical? What's numerical? What can we simulate? What can we estimate from experimental data? So here's the punchline. Basically, we've been studying information and understanding how that gets generated by nonlinear dynamical systems. Now we're going to talk about a related but complementary notion, computation. And that is how we're going to talk about structure, oddly enough. The way to kind of draw the contrast, and this hopefully will take on more meaning as the weeks go forward. So how nature is structured, the organization that we see around us, is actually a reflection on how nature is computing, storing and processing information. So I'm going to try to stitch together these two ideas. the organization, regularities, symmetries that we see around the world, those are actually reflections of how nature is storing and processing information. That'll be the claim. You can disagree with me, but that'll be the claim. So these things all get tied together. So the goals, well, we've hit 2 of them already. Presumably, y'all can go out and sort of identify sort of mechanisms of instability, potential chaos. Right? The Honda ad, you can now have a different notion of the role of instability there, and we have ways of quantifying that. So now what we're going to do is analogous goals, but really focus in on how to identify and quantify structure. What is pattern in the world? And then relate both unpredictability and structure to this extended notion of what I call intrinsic computation. Let me skip a few things here. There are lots of applications. If you understand how arbitrary processes can store information and do computation, then maybe you can come up with whole new substrates for building computers, harnessing that. Go back to analog computers. Think about in the quantum setting, what kind of nano-scale devices can we now build when we have this, we're sort of unshackled from this digital hegemony of current computation, and there's this generalized notion that we have. We can then sort of look around for that. And also it gives maybe more scientific implications, thinking about how evolutionary systems produce biological organisms, how a form is similar or different from the function of the organism. And if you're a big fan of automated data, you look at these ideas and you go, boy, we should be able to apply this to the petabytes of data coming out of spontaneous formation of social networks on Twitter and Facebook and all that sort of thing. Try to actually have a system that will actually aid, well, hopefully natural scientists producing theories and for more and more complex systems. So I'm going to skip ahead pretty quickly here. Well, I won't go over this, but just since some people are new. So we have Karana, who is sitting in the back. She and Alex sitting in the back will be TAs, and then Ryan will also kind of TA, but he's running the server that has all the homeworks and stuff on it. So, and maybe next week I'll try to ask some more questions about who we all are. Again, of course, website hasn't changed. This is where everything goes through. Everything. I put announcements up probably twice a week there on average. When the homeworks are up, how to get information, how to enroll, all that sort of thing. Here are emails. And of course, all the lecture notes are online at the website. Just go to lectures. There's an outline. There's a PDF of these lectures. When this gets finished, there'll be the slides with voiceover. So we're recording that now. There's also an HD recording. And I put the slides with voiceover up on YouTube, and then there's another link for the HD, so you can see the lecture again.
Even for last quarter?
Yep, it's all there, yeah. Except, as we recall, a few screw-ups. Yeah, and then there's another group of students down at Berkeley that are also taking the class, so that's for them and us. Yeah, so it's all going into the ether here. Office hours, Wednesdays 3 to 4. And Ryan and Corana want to update theirs, so look at the homepage for the class. Okay, the website has readings, number of readings. I think I mentioned in one slide what to read for Thursday. The homeworks are up there. So the homeworks are all announced and done online through a web browser. So there's a system called Sage. It's documented at sagemath.org. But you can go to the top of the course homepage. It says CMPY Campy Server. You go there and there are instructions on how to log in. And then you can just send Ryan an email and he'll set you up with an account. I think everyone else, you need an account. Yeah, so do that. And then, like I said, every Tuesday I will put up the homeworks for the week. They're due a week later. And what you'll see is there's a little tutorial you should go through with Campy. And you might need to get some help from Ryan or Karana or Alec to get started. There's moderate amount of ramping up, which everyone else has done and kind of suffered through. So, yeah. So, but the point is, don't hesitate to ask. There's stuff to learn, and maybe even sitting down with Ryan or Alec or Karana for a half an hour just to get started would really accelerate things rather than kind of get frustrated with things that aren't obvious. So. Well, that was winter, so that's all done. So spring is different than having the exams and the homeworks. Basically, it's just homeworks. We'll do maybe half a dozen homeworks. You're going to start using the computational mechanics in Python routines and packages in much more detail. So there'll be helper labs that you go through first before you do the homeworks. Some of them also just kind of parallel the lectures, so you can see how some things work out. And then there'll be a project. So first half a quarter, homeworks, and then I'll be kind of pushing you, probably starting week 3, to think of a project, right? Some kind of, choose some dynamical system, space-time, low-dimensional chaotic system. Maybe if you're a statistical physicist, you want to do a spin system, some network system, your choice. Could be spike trains, whatever. Choose some system, and then the project will be to maybe write some simulation code or something like that, analyze these computational and informational properties. So, and then the question is, of course, what do they tell you? That's the key thing. You can just do this stuff. Presumably, they will tell you something new about the system. Yeah, right.
Does it have to be a real system?
Real?
Like an actual...
You're asking me? Real? I don't do real. Yeah, no, that's fine. Whatever. I mean, it could be real. Could be real. well, actually, so yeah. So, well, Christina actually kind of did a real. She put together last, was it year before winter, an analog computer that simulated the driven van der Pol oscillators. So that was sort of a simulator in a sense, but it was real physical circuits. She did it over in the lab. It was I enjoyed the project, yeah, you actually put together this circuit that solves the van der Pol differential equations, and you have a sine wave generator, and you can hear it go chaotic and make all sorts of strange noises. And
you have to argue that it relates to anything useful?
No, not at all.
Cool.
No, I mean, yeah. My typical role in choosing the projects is that they're tractable. I mean, be careful. These are nonlinear, complicated systems. They can be dissertation topics, which I think your spring project is such a thing. Yeah, that was a biological project on tendrils that vines send out to grab onto each other, which maybe you can mention at some point. But yeah, so actually, where is it? Not here? Well, anyway, at the bottom of the homepage, there is a description of the projects, roughly what these get some sense, but also the list of all the previous year's projects, so you can get some idea. There are 30 or 40, more than that, projects down there. Get some sense of what people have done. The reports are there, the presentations. The project will be concretely a little presentation to the class, say 15, 20 minutes at the end of the quarter. Since we have folks at Berkeley, what I've done is found a place that's halfway between Davis and Berkeley, so we're going to have like an all-day conference, barbecue conference, where we'll do this. It's down in Martinez, which is actually accessible by train. And I'll give you more information on that. And some kind of written report, code if that was involved. And definitely take a look at what else was there. But like I said, often I'm trying to simplify things and make them tractable in just a few weeks. So that's my role, is to simplify. Books haven't changed really. We're not actually done with Strogatz or Cover and Thomas. Even the homework that I put up last night for this week, still doing some things in Cover and Thomas to set us up for next week. But you might think, when you're thinking about projects, certainly going back and looking at some of the exercises at the end of the chapters might stimulate things. There's interesting models in there. Biological, chemical, electrical circuit models would be perfect to analyze. And of course, yes, lecture notes are online. Also, all of the articles and supplementary articles, published articles that we'll read, and other things are there at the website. So like I said, since you folks are new, I really think you should get some direct help with the Sage and Campy servers. Hopefully you've had some experience programming a little bit. Python?
Yeah.
Python? It's a language, Python. Okay. Definitely we'll talk to Alec or Karana or Ryan. Yeah. Right. Yeah, so this is the URL for that server. It's actually linked on the top of the page, so there's just a thing you hit, and it takes you there. And there's even a link on the page you go to of how to, Ryan's email and how to set up an account there. So reading to do, I went a little bit over here. So between order and chaos is this recent Nature Physics review I wrote. That will give you an overview of what's coming up. Skim it. You don't have to do in-depth because that's going to take us 5 weeks to cover it. But just to get some sense of where we're going. Also, computation mechanics, pattern and prediction, structure and simplicity. Just the introductory sections of that might help orient you a bit. And for fun, take a look at this Stanislaw Lem, Polish science fiction writer who just passed away half a dozen years ago, but he actually knows information theory and statistics. So he has this nice New Yorker article called Chance and Order. That'll bring up some of the questions, or reframe some of the things I said already. And there's a quick, very, very newsy, readable New Scientist article by Mark Buchanan that kind of talks about this idea of reconstructing order from chaos. Okay.